You've probably heard that rainbows are formed by light interacting with raindrops, but did you know that all rainbows form as a result of that light bending 42 degrees inside the drop? In this video, I'm going to walk through a quick proof as to why by looking at the physics that takes place inside of a raindrop. But first, I need to explain a few things about how light rays interact with the environment. When light hits the surface part, that light reflects off symmetrically like so. Mathematically, we say that the angle of incidence θ1 is equal to angle of reflection θ2. But for less reflective surfaces, light is not entirely well reflected and some travels beneath the surface and into the medium itself. This process is called refraction. Refraction obeys this equation, which is called Snell's law. The theta's represent the angles between the light rays and the line perpendicular to the surface, which physicists called the normal line, and the ends represent something called the index of refraction, which is a measure of how much light ray bends when passing from a vacuum into a particular medium. For air, the end value is reasonably close to 1, which means that light hardly does any bending as a result of the density of air molecules, and for water, the material that makes up a raindrop, the end value is about 1.33. But physicists like to be ideal. We'll call that quantity 4/3. There we have an equation for how light refracts into a raindrop. So without further ado, let's take a closer look at what happens to the light inside of a raindrop. A typical raindrop is roughly the shape of a perfect sphere. When light from the sun interacts with the raindrop, it initially refracts, then reflects off the back of the droplet, then refract out. Again, I'll draw the normal lines and a few parallel to the line of internal reflection to make the incoming geometry a little bit easier. Let's call the incident angle phi and the refraction angle beta. Our goal is to use geometry to see the relationship between these two angles, because angle of incidence is equal to the angle of reflection. With respect to its own normal line, we know that this angle is also beta. Now, something important to note about Snell's law is that it actually works regardless of which way the light is traveling. So if you don't mind, I'm going to surreptitiously reverse the direction of these light rays. Having done this, we can see that this bottom angle must also be phi, because it's angle between incident light and the light that experiences some bend upon entering water. That's just how we just define phi. So by definition, this refraction angle has to be beta, and by the same logic as we saw above, angle of reflection with respect to its own normal is beta as well. Now let me draw your attention to this triangle for a second. Since the sum of the interior angles of a triangle is 180 degrees, this angle has to be 180 minus 2 times beta, and since two angles on horizontal line should add up to 180, that means that this blue angle also has to be beta from geometry. Then we know that this top left angle must also be beta. Thus, the angle between phi and 2 beta will have magnitude of 2 beta minus phi. And all that having been done, we finally have an angle between the incident ray and its normal, so we can apply a Snell's law like so. Of course, true understanding requires working through the algebra yourself. So if you feel up, go for it, and pause the video and give it a go yourself. I, however, will skip the part to save some time. Great. Now we have a general function for phi as function of the angle between angle beta. When we plot one against the other, we get this graph with a noticeable peak. As it turns out, this peak corresponds to the magical pair of angles which causes rainbows. Now, if you're like me, you might be thinking, why would it be this particular peak? This graph represents the variable magnitude of the angle between the horizon and the sun. It doesn't have anything to do with the intensity of the light, the size of the raindrop, or any type of physical quantity that one might expect. to be tied to scattering of light. But as it turns out, the reason for the rainbow's presence at this particular point is not into the angles maximum per se, but more so that this point happens to be the flattest. That means that a relatively large change in beta around this point corresponds to a relatively small change in phi. This means that many different values of beta can all get focused into about 2 times the angle, and that reason that angle is doubled is because that light gets refracted twice. What's going in and what's going out. So let's find out what the angle is. We can find the flattest point on the curve by setting derivative equal to 0. Alright, let's do a little rearranging. Now we can just plug this part into the Wolfram alpha and be done. But there's somewhat interesting step in the algebra here that I think is worth examining. When we square both sides, we can take advantage of the fact that cosine squared is 1 minus sine squared. Then after making that substitution, we have enough information to solve this equation purely analytically. In the final step, we receive beta value of about 40 degrees, which when plugged into the phi equation yields a value of about 21 degrees. In doubling that angle finally lets us see the magical level of angle 42 degrees. But there's something I haven't explained yet. Why does light spread into different colors rather than remain monochrome in white? The reason for that is that in reality water does not have just one index of refraction. It actually varies based on the wavelength of the incident light. So the red component of the sunlight, for example, gets refracted at a different angle with violet component, which gives us the nice spread across the visible spectrum that we could come to expect from a rainbow. I've exaggerated it in this animation, but you get the idea. One last thing, if the light refracts twice inside the raindrop rather than just once, we see a double rainbow, which will form about 51 degrees. Much like the first rainbow's 42 degrees, the mathematical derivation is largely identical to what I've just shown. But if you want to see it yourself, I highly encourage you to pause and think about it as you go. And there you go.